Today we are exploring why larger models learn more. A paper that asks why increasing model size lets a network learn rare and complex tasks that a smaller network misses, even after seeing enormous amounts of data.
We already know that larger models usually achieve lower loss. What is still unexplained?
Earlier scaling law work describes how average loss falls with model size and data, but an average hides the composition of learning. A small model may master frequent, easy patterns while completely failing on a rare skill, and the loss curve alone does not explain why. The paper makes a stronger claim than saying a bigger model learns faster. It argues that some loss reduction requires model scaling. There are parts of the data distribution that a smaller model cannot learn even in the infinite data limit.
How does the loss diagram separate a data shortage from a model size limitation?
Follow the smaller model down to its asymptotic loss. The first gap closes when that model receives more data. The remaining gap does not. The larger model reaches a lower loss because its extra capacity makes additional parts of the distribution learnable. To explain that gap, the authors build a controlled mixture of tasks. Each task has a frequency and a set of useful feature directions. A shared encoder has limited width, so all tasks compete for the same neurons.
What decides which feature directions win that competition?
The key quantity is feature utility task frequency multiplied by that feature's signal strength. The optimal width then encoder retains the highest utility directions. Frequent features tend to rank high, while rare or complex tasks need more width before their features survive.
So a smaller network might be able to represent a rare task in principle, yet still allocate its neurons elsewhere during training.
Exactly. The bottleneck is data-induced competition, not merely whether some set of weights could express the task. With limited width, gradient-based training favors directions that reduce the most mixture loss, so common or simple tasks take the available slots. The second part of the explanation is interference. Frequent task updates arrive repeatedly. In a narrow model, those updates overwrite the weak feature traces created by an occasional rare task example before the next rare example arrives.
Why does adding width reduce that overwriting?
Once a wider model represents the frequent tasks well, their remaining error becomes small. Their gradients weaken, so they stop pushing as hard against rare task directions. Rare features can then persist between observations and accumulate over time. The paper formalizes this with the frequent task residual, the signal that frequent tasks still need the encoder to explain. It proves that when width makes this residual small, the magnitude of the aggregate frequent task gradient is also bounded and small.
What do those two expressions tell us in plain language?
The residual measures how much frequent task structure lies outside the encoder's current subspace. The bound says that after a wide model captures almost all of that structure, frequent task updates cannot strongly disturb other directions. That gives rare features room to survive. The first synthetic result tests the utility rule across 32 regression tasks with power law frequencies. The heat map shows a staircase. As width increases, the model first retains high frequency features, then progressively reaches lower frequency tasks.
Does the utility rule only describe the ordering, or does it predict the amount of loss too?
It predicts both. On the right, observed per task loss closely tracks the analytic prediction across several frequency skews. That agreement supports the claim that width is spent on the highest utility task features, rather than being shared evenly across all tasks. Next, the authors directly vary the frequent task residual. The purple line shows that the most frequent task remains strongly represented. The orange line shows that the rarest task appears only after the residual falls below a critical region.
What is the important comparison around that critical region?
Below the threshold, the rare task signal is positive and can be retained. Above it, the signal collapses towards 0 or below, even for wide models. So width helps because it reduces unfinished frequent task structure, not because size automatically protects every rare feature. The decisive mechanism test holds total rare task frequency constant but changes the gap between rare observations. After each rare task injection, narrow models briefly gain rare task signal, then frequent task updates erase it. The widest model keeps the signal and steadily accumulates it.
Why is matching the total frequency important for this test?
It separates exposure from retention. Every setting receives the same total amount of rare task data. The difference is whether the model preserves each update across the intervening frequent task batches. Larger gaps hurt narrow models most because they allow more overriding before reinforcement arrives. Synthetic tasks make the mechanism measurable, but the paper also tests whether it survives realistic language model pre-training. The authors train OLMO models from fermillion to ferbillion parameters and inject comparison and modular addition tasks at controlled frequencies.
What happens when those injected tasks become very rare?
The heat maps show a clear size by frequency boundary. For the comparison task, at a frequency of about 2.4 times 10 to the minus 7 per token. The 4 million model stays near chance, while the 1 billion model reaches about 65% test accuracy. The modular addition task is harder. At its highest tested frequency, the 20 million model achieves about 1% accuracy, while the 4 billion model reaches about 85%. At lower frequencies, even the largest tested model struggles, showing that scaling shifts a boundary rather than eliminating it.
Could those results simply mean that rare examples arrive too late, rather than being overwritten?
The matched frequency language model experiment addresses that. The authors inject the same number of task examples either frequently in small batches or rarely in large batches. Larger gaps produce worse evaluation loss, despite identical overall frequency, which directly shows that retaining updates between observations matters.
Do the internal representations on gradients support the same explanation?
Yes, larger OLMO models encode more task-relevant features. The authors then localize the task circuit, finding the first MLP layer has the strongest causal effect, and compare task gradients with gradients from ordinary pre-training tokens on the most task-relevant neurons. In larger models, full-batch gradients carry more of the rare task direction, while non-task gradients show little or no opposing interference. That mirrors the synthetic mechanism. Ordinary updates are less likely to erase the fragile task circuit before it can strengthen.
What should we be careful not to overclaim from these experiments?
The strongest causal evidence comes from synthetic mixtures and deliberately injected tasks, where frequency, complexity, and gaps can be controlled. Those results support a general mechanism, but they do not prove that every natural language skill follows the same clean utility ordering.
Then what is the clearest takeaway for choosing model size or constructing a training mixture?
Do not judge a model only by whether it can represent a task or by its average loss. Ask whether the task appears often enough, whether other tasks monopolize the feature budget, and whether ordinary updates erase the task before its next examples arrive. The paper's central answer is that larger models learn more because it changes the competition dynamics of training. They fit common tasks, weaken the gradients that cause interference, and preserve rare or complex features long enough for those features to accumulate into a learned task.
So scaling changes not just how much a model stores, but which weak signals survive the training process long enough to become useful.
Exactly. That is the paper's data-centric explanation for why larger models learn more. Thanks for watching, and that wraps up our paper walkthrough.